In this video,
This video is about transient response analysis.
We talked about
in the last couple of
transient
weeks, we have
response
seen some
transient
transient response analysis, and then I moved on to control design
these transient
and how to
response
use
characteristics
can be
used
characteristics
to
specify
specify
design requirements on your control we never really finished talking about transient response.
there were some
and,
points that I
like to just
did not
review
cover
it
when
before
talking about transient
pointing out
response.
a
So
couple
here's
more
a
details.
quick example
from,
to refresh
where we left off the last time. Now here is this example that you see on the screen is from your previous homework. This is a 2-mass spring mass damper suspension system, and it's a 4th order system, as we have seen several times. The A and B matrices are what you see here on the screen. These were derived in the notes, and in one of the homework problems I gave you these numbers that you see over here. So in this example, I'll just walk you through this example about how to find the transient response characteristics. There are a couple of ways to do it, or a couple of ways of looking at it really. It gives you the same answer. One way is, of course, to just look at the A matrix and find everything based on the eigenvalues of the A matrix. So you don't even need to look at the B matrix. But the other way, of course, is to go through the transfer function and try and acquire some standard forms as the first and second order responses, and we'll take a look at that as well. If I plug in the numbers of the spring mass and damper, or spring and mass damper coefficients, and the masses into the A matrix, I get this A matrix. And the first step, as you may recall, is to find the eigenvalues of the A matrix and see what mode structure this has. So you can do this in MATLAB. It's a 4th order system, so kind of difficult to work out by hand. But if you work out the eigenvalues, you'll get the following numbers. So you'll get 2 real eigenvalues. One is 5.0804. The second one is negative 3.884, and the other one is a complex conjugate pair. So I'm just going to write it as 3, 4 because they're not really two separate. I mean, they are two separate numbers, but we are going to treat it as one single mode, as I discussed previously in class. This is one single second order mode, so I'm going to write the eigenvalues together, and the eigenvalues sort of work out to negative 0.1558 plus or minus I 2.1. So these are the 3 eigenvalues, and the first thing that we note is that all eigenvalues have real parts, which is good news because that means that the system is stable. So let's make that note first. All eigenvalues have negative real parts. Those are minus 5.8 something, minus 3.8 something, and then this one has the negative real part of minus 0.15 something. So that's one observation. The second observation is identifying the modes of the system. So let's identify the modes. We see lambda 1 over here. That's a first order mode. It's one real eigenvalue. So lambda 1 corresponds to a first order mode. Same with lambda 2, also corresponds to a first order mode, just one real eigenvalue. And finally, lambda 3 and 4 together, they constitute a second order mode. Now that we have identified these modes, let's go ahead and find the transient characteristics associated with each of these modes. Let's look at the first one, lambda 1, negative 5.804. That's a first order mode. So even before I actually work out the overall impulse response and step response and such, I know the general form of the impulse and step response. So the step response is going to look something like this. Step response will look something like this, and the impulse response is going to look something like that. Okay, so that general shape I already know, and the exact value of where the step response stabilizes kind of depends on the overall transfer function, but we'll talk about that soon. All we need to do for now, or the information that is immediately available, is the rise time and the settling time. So this is the rise time over here, and this is the settling time over here. So the rise time is 3 over the real part of lambda 1, which is 3 over 5.804, and the settling time is 4 over the real part of lambda 1. In this case, lambda 1 is real, but just make a note of the absolute value. So although lambda is negative, you're looking for the absolute value. So that's why no negative sign over here. But anyways, this is 4 divided by 5.804. And these values work out to 0.5169 seconds and 0.6892 seconds respectively. So what this means is this is 0.6892. So the step response of this mode settles to its final value in a very short amount of time, in only 0.68 seconds. So it gets within 2% of its final value in 0.689 seconds. So that's what this means. And again, this is a first order mode, so there is not that much to analyze, and we're kind of done. So these two numbers are what characterize this mode, pretty much all of it. And then we can move on to the second mode. Moving on to the next mode, we have lambda 2 equals negative 3.8844, and as before, this is a first order mode, so very easy to understand and analyze. I'm not even going to bother drawing the picture again. We can directly calculate the rise time and the settling time as before. So 3.3844, 4 divided by 3.8844, whatever that. These work out to the following. This works out to 1.0298, almost 1.03. And this works out to 0.7723. Now, let's draw a bit of a comparative picture between this mode and the previous one. Now remember, for the previous one, we got the settling time as 0.6892. So let me just write that number down here, 0.6892 for the previous mode, which is also a first order. So now if I try and plot the two modes together, just to give you an idea of what we're looking at, only the step response here. So let's say this is 0.6892 over here on the time axis, and we have almost the double of that, 1.0298, nearly the double of that, but not quite. So the first mode, the one with lambda 1, settled very fast. So it went like something like this. So by the time it got to 0.689 seconds, it was already near its steady value. Now the second mode, the one we're looking at right now, is slower. So it's going to look like this. It's going to take a while to settle down. And that's the difference. Now, The overall response of the system is going to be something like a weighted mix of these two, weighted sum of these two, and the weights uh, that make up the entire response, those need to be determined from the transfer function, and we'll talk about that later. But for now, as long as we are interested only in the individual mode analysis, this is it. This is the picture that we look at. And the reason I'm drawing this picture is because you can already see that by the time we get around here, let's say something between 0.68 and 1 second, the first mode doesn't really matter anymore. It has already settled and it's not really being transient anymore. It has already settled to a constant value. So all the transient after that is due to the blue mode, which is with this lambda 2 eigenvalue associated with that eigenvalue. So I'm drawing these pictures just to make you aware of the different time scales that each mode works on. And the reason we should be interested in these different time scales is because that affects the control design. Sometimes you design different controllers to address different modes, and those different controllers address also the different time scales. So one of them works really fast. So for example, if you're interested in changing the first modal characteristic, that's a very fast controller as opposed to this one, which is somewhat slower. And then we'll look at the third one, which is actually much, much slower. So its settling time is much larger. So part of the objective of this video is to show you the different settling times of different modes and what it means to say fast mode versus slow mode. Moving on to the next mode. Now, like I said before, this is a pair of complex conjugate eigenvalues. So this constitutes a second order mode, and this requires a little bit more work than before. So the step response of this mode on its own is going to look something like this. So it's going to be a mix of exponential decay and some oscillations. Okay, so those happen due to the complex conjugate part. And there are a bunch of characteristics associated with it. So there is a settling time, which is when the mode dies down to within 2% of its steady state value. And this settling time is given by 4 divided by the absolute value of the real part of this eigenvalue. Now the real part is 0.115, so that's something we'll calculate. Then there is the peak time, which is here. It's an exponential decay, so it only hits a peak once and then decays. The amplitudes keep decaying after that, like this. So this is the point where it reaches the peak. So that's the peak time. That's given by pi over the imaginary part of the eigenvalue. Again, absolute part of the imaginary part, absolute value of the imaginary part. And then there is the peak overshoot itself. There is the peak overshoot itself, MP. And we'll discuss this in just a second. And the final thing is this rise time, the first time when the response hits its steady state value. So that's the rise time, which is the main thing that's different from the first order response. The first order response never crosses the steady state value, so you don't really have a rise time that looks like this. So in that case, the definition is slightly different. It's within 90% of the steady state value. Anyways, so we have these quantities. Let's do the easy ones first. Let's have settling time as 4 divided by the absolute value of the real part, which is 4 divided by positive 1 point or 0.1558, which works out to 25.67 seconds. So that's a very large settling time. Now, comparatively, the other two modes had a settling time of 1 second or less. So you can see that this is much longer on the time scale, in that it takes a long time to settle down. So We call this the dominant mode for this reason, because it's going to dominate the overall response of the system. So when you plot the overall impulse or step response of the fourth order combined system in MATLAB, for example, you'll find that it actually looks very close to what the second order modal response would look like. So it's almost as if um, the overall system was behaving just like a second order system with these eigenvalues. So that's what we mean by dominant mode. Anyways, moving on, we have the settling time is 25 seconds. Let's calculate the peak time. That's also easy. Pi divided by the absolute value of the imaginary part, and that's pi divided by 2.1, which works out to around 1.496 seconds. So that means this guy over here, this value is 1.496 seconds. So remember the blue and the red mode from the previous two slides, the first order modes, they died off at before 1 second. So they were dying off around 1 second over here, whereas this mode is just about reaching its peak at 1.5 seconds almost over here. And it takes a very long time to settle down after that. So that's the peak time, and then we have the rise time and the maximum peak overshoot. So we'll calculate that next. Now to calculate the rise time, we have this formula. We have 1 over the absolute value of the imaginary part multiplied by tangent inverse of the imaginary part. Now this is where we need to be slightly careful. On the numerator we have the absolute value of the imaginary part, and on the denominator we have just the real part, not absolute value. Okay, so that's the definition. Now the other careful thing that we need to do here is that this is a 4-quadrant tangent inverse. So tangent inverse is not it doesn't give you a unique answer. So you can have two different angles with the same tangent. So we need the 4-quadrant value. The default on most calculators is the 2-quadrant, which is between minus 90 and plus 90 degrees. And if you do that, you're going to get a slightly different and incorrect answer. So if this is the 4-quadrant tangent inverse, the best way to do this is to use the atan2 function in MATLAB. atan2, that's arctangent in the 4 quadrants. And the way that works, the syntax for that is just something like this, comma, the real part. And if you work that out, the whole rise time works out to 0.783 seconds. So that's the rise time. And finally, the maximum peak overshoot. Now there is an easy formula to do this, which I neglected to give you in class, but I wrote it down in the notes, and that's minus the real part of the eigenvalue multiplied by pi divided by the imaginary part, both absolute values again. So this in this case will be e to the minus 0.1558 times pi divided by 2.1, and that works out to 0.7921. Okay, so what does this mean, this 0.7921? This means that the peak overshoot is 79%, 79.2% of the steady state value. Okay, So what this means is, remember how we had the peak overshoot that looks something like this. That's a terrible picture. Something like this. So compared to the steady state, this bit is 79% higher. So that's a very large overshoot. Okay, so it's saying that if this quantity is 1, then this quantity, the overshoot is almost zero point 0.8. So that's a very large overshoot. It almost shoots up to twice of its steady state value before settling down. So this is not a very ideal step response. So if you had a suspension system that was actually like this, you would have a very uncomfortable ride in the car. Let's put it that way. But anyways, as far as calculating all of the transient response characteristics, that was a straightforward example. There are some more details which I'd like to point out in the next video or so.